Hello and welcome to another video on orbital mechanics. I'm going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition. I'm up to problem 2.37, and problem 2.37 says a meteoroid is first observed approaching the Earth when it is 402,000 kilometers from the center of the Earth with a true anomaly of 150 degrees. If the speed of the meteoroid at that time is 2.23 kilometers per second, calculate A, the eccentricity of the trajectory, B, the altitude of closest approach, and C, the speed at the closest approach. So let me get on with it. 2.37. So first part A, the eccentricity of the trajectory. That first thing we need to do, what we can do, is get the semi-major axis, and we have a formula for that. It's the energy formula. So if you say V squared over 2 minus gravitational constant over R equals gravitational constant over 2A, and we simply rearrange for A, we'll get A equals R gravitational constant over V squared R minus 2 gravitational constant. And if you work, we are given R in the question. It's 402,000 kilometers. We're given V. It's 2.23 kilometers per second, and mu is Earth's gravitational constant. So that gives us A, which comes out 1.33 by 10 to the 8 meters. And then from that, we can get the eccentricity. This is a little bit more complicated because it's not as simple as just filling in the values. We have the equation R equals A E squared minus 1 over 1 plus E cos theta. So they've given us theta. Theta is 150 degrees. Again, we have R, we have A, but we don't have E. So we have to rearrange this. And there's an E squared in there. And what happens is when we rearrange it, we end up with 0 equals E squared minus ER over A cos theta minus 1 minus R over A. So that's what that turns into. This is a quadratic equation, so our constants here are 1 in front of the E squared, and then R over A cos theta, and then that's B, and minus 1 minus R over A is our C component. So if we were to work this out with the quadratic formula, we'd see that E equals minus R over A cos theta plus the square root, well, plus or minus the square root of R over A cos theta minus 4. A is 1, so we'll ignore that, upon minus 1 minus R over A over 2A, which is just 2. Yes, if you work that out, you get E equals 1.086 on the plus side, and on the negative side you get minus 4 or something, which is not right. So this is the correct eccentricity. Now that we have the eccentricity, we can get the, well, that's what I asked for. That is part A, sorry. Yeah, and then part B is the altitude at closest approach. So that is our periapsis. That is very simple. We have a formula for that. That is radius of periapsis equals A upon E minus 1, which is just one of the radius formulas simplified with the theta equal to 0. And that gives us RP equal to 1.147 by 10 to the 7 meters. And then the part C is the speed at the closest approach, and this is again just filling in the blanks. Our velocity at periapsis is equal to the square root of our gravitational constant over semi-major axis and plus 2 gravitational constant over Rp. And that is just the energy equation rearranged to give us the velocity, which equals 8.516 by 10 to the 3 meters per second. And that is 2.37. If you, the MATLAB will be in the description below. If you think I've made a mistake or if you have any comments, please leave them below. Thank you very much. Goodbye.